So here's another rate law problem for this reaction. That is what we have to calculate. Remember, a rate law is universal for the reaction at a given temperature, in this case 700 degrees C, and it depends on the concentration of the reactants and whether they decay with zero, first or second order kinetics. It also depends on the rate constant lowercase k. So don't get enticed by the fact that you see the 2's here, that the rate is somehow going to be this form. That you can put a 2 here and a 2 here just because you see a 2 here and a 2 here. Now, that's incorrect. If it's a 2, second order decay, you're going to have to do the math here to show it. So comparing the three experiments, you see in this first and second experiment, they kept NO reactant the same, but they decreased H2 reactant. Between experiment 1 and 3, they kept H2 reactant the same, but they looks like they decreased by some factor the NO reactant. So, you know, you increase one, keep the other the same. That's pretty much how you do calculate the rate law. So our goal here is to calculate K, X, and Y. The order of the reactants are going to be X and Y. The overall order of this entire reaction, by the way, is going to be X plus Y. So looking at this, let's compare experiment 1 and 2. All right, the rate law for rate 1 is going to be K times H2 concentration to the power of X times NO concentration to the power of Y. Okay, same thing with rate 2, experiment 2. Okay, now let's plug in numbers that we get from our data table. H2, experiment 1, rate 1 is 0.010. Rate 1 for experiment 1 is 2.4 times 10 to the minus 6. And let's just start plugging those numbers in. All right, I plugged in our numbers here. So the lowercase k rate constants cancel. We have to calculate this at the end of this problem. And the 0.025 to the power of y cancels out with the 0.025 to the power of y. So we're left with 0.01 divided by 0.005. That whole thing is to the power of x. That is equal to 2. So that's going to equal to 2 to the power of x. 2.4 divided by 1.2 is going to be 2. Okay, right? So 2.4 times 10 to the minus 6 over 1.2 times 10 to the minus 6. I can do it in my head, and it's going to be 2. So this looks to me like is going to decay by first order kinetics, right? X is equal to 1. H2, I should say, is going to decay by first order kinetics and the associated equations that come along with it. All right, now we're going to do order of reactant NO. I'm thinking about picking experiment 1 over 3. It really doesn't matter what you do or whether it's 3 over 1 or 1 over 2. We just want to make life a little easier, and I believe just by eye, comparing 1 over 3 is the best. So let's do our same situation now, comparing experiment 1 over experiment 3. Comparing experiment 1 over experiment 3 here, and you can see by comparing 1 to 3, the 0.010 will cancel out. So that's one of the reasons why I picked that one. So the k's cancel. We already figured out x to be 1, but that's a moot point here because the 0.010 to the power of x cancels. So we're left with 0.025 divided by 0.0125, all of that to the power of y. So this also is 2 to the power of y. And 2.4 times 10 to the minus 6 divided by 0.60 times 10 to the minus 6. So what's 2.4 divided by 0.6? I feel like I should be able to do this in my head. 4. Okay, that makes sense. 4. So this decays via second order kinetics. Y is 2, right? 2 to the power of 2 is equal to 4. So this is second order kinetics. Right? So we're not done yet. We need to figure out an actual value of k, the rate constant, but let's fill out with what we have for now. So we have rate is equal to k, which is what we need to solve for next. H2, we figured that it decays by first order kinetics, and then NO, we just figured out decays by second order kinetics. So don't go by the balanced chemical equation. The balanced equation is totally different. We calculated this experimentally. All right, how do we figure out K and making sure it's in the right units? By the way, the overall order of this reaction is 3. 1 plus 2 is 3, so the overall order is 3. Pick any experiment, find K by solving for it. So I'm going to pick experiment 1, though you can use experiment 2 or experiment 3, it really doesn't matter. And units, units, units. This is super important, super critical. You have the right units. Equals K, which is what I'm trying to solve for. 0.010 to the power of 1 is just giving me 0.010 big M. And NO squared, so that's 0.025 squared. Just do 0.025 squared on our calculator. So 0.025 times 0.025 is 6.25 times 10 to the minus 4 M squared. So 0.025 squared is this value, but we also have to square the M. So it's M squared. The total is M cubed. And alright, so now to solve for K and making sure we have the right units, we're going to take this and divide it by there. K is going to equal to 2.4 times 10 to the minus 6 M molar over second. Okay, this going down by division is going to be 6.27 times 10 to the minus 7 M cubed. Check out what's happening here. K is equal to one of these M's is going to cancel out with one of these M's, leaving me with M squared. So K is going to equal to 2.4 times 10 to the minus 6. 2.4 times 10 to the minus 6 divided by 6.27 times 10 to the minus 7. 3.82, let's do 3.83. Make sure we have the right units now. 3.83, and in the denominator it's going to be M squared. In the denominator it's going to be seconds. In the denominator will be M squared. In the denominator will be seconds. So that is our value of K. Finally, we can write our right answer, and this is the answer that you will need to write on any type of exam or so. Our final answer is going to be rate is equal to K, which we already solved for, 3.83 divided by M squared times second, or you can say M to the minus 2 seconds to the minus 1 times the concentration of H2, okay, which we have figured out to have first order kinetics, times the concentration of NO, which we have figured out to have second order kinetics. So this is your final answer. We can test this, sort of a validation. Let's take experiment 2 values and see if we get the same rate. Or we can take experiment 3 values and see if we get the same rate. So let's just do experiment 2 conditions. Experiment 2, 0.005 raised to the power of 1 times NO is 0.025 squared times 0.025 squared. That's that, times our rate constant, 3.83, times 3.83, and we're getting about 1.2, 1.19, so 1.2 times 10 to the minus 5, yeah, it matches 1.2 times 10 to the minus 5. So we're good, and pretty confident experiment 3 conditions will also satisfy that this rate of 0.60 times 10 to the minus 6.